So let's dig into this 20th century crisis one by one, and let's start with blackbody radiation. Okay. So let's talk about blackbody radiation first. What is a blackbody? I would define it as, let me draw it in black, although it's not necessarily in black. That's a bit misleading, I'm aware of it. Blackbody is something that does not reflect light. Doesn't reflect light. So we call it blackbody because normally we see colors like your skin tone and the fact that this is yellow, etc., are usually related to which colors the objects reflect. Okay. Hence, something that doesn't reflect light has been called blackbody. But the thing can shine light by itself, not shine, radiate light. Are you radiating light? Yes, you are also radiating light. It's just not in the visible range, right? If I put this infrared glasses, I will see that you are glowing, just like the sun, right? So the sun is a good example of blackbody. So what happens is that light, if you shine light to the sun, it will not bounce off the sun and come back to you, right? It will get absorbed in the sun. It will become, it will heat it up a little bit, and then because of that heat, it will be released later on, maybe as a different frequency, light. But at the end of the day, a blackbody is a perfect absorber and perfect emitter. Perfect absorber and perfect emitter at the same time. Emit is with one M or two M? Kirchhoff's radiation law, very good. Let's talk about it. As far as I remember, it tells you that the radiation depends, it's an observation, that the radiation depends only on the temperature of the blackbody.
Or Stefan Boltzmann?
No. Stefan Boltzmann is T to the 4. Yes. Kirchhoff's okay. Can you check it? Because as far as I know, Kirchhoff's law is... Can you check it still? I don't trust you. Okay. Doesn't matter. The point is that why do we care about the reflection, no reflection stuff? Because we want to see the radiation profile only because of the interior temperature of the object. Does it make sense or not? So if it reflects, then it can shine. It can send you light because of the reflected light. So we are getting rid of it. It's just only the light that comes out of the body that is due to its temperature. So far, any questions? Yes. Yes.
Nature, so it's normal to receive some radiation from the black body crystal?
No. The radiation, okay, nobody is perfect, I agree, but Like for a physicist, when something is 10 times larger than the other thing, we just say it's infinitely larger with respect to the other one, right? Parallel plate capacitors, we assume that electric field lines are perfectly uniform, and our calculations support it. So for the sun, I don't know how reflective the sun is, but I'm assuming that it's not reflective at all, like 0.0000001% of reflection. But the light that we see comes out of its inner workings, its temperature. Okay? So the light that we see is the light it produces itself. Okay? Good. Very good. So far, so good. And we basically developed towards the end of the 20th century, no, 19th century, we developed these various tools which would give us this, right? This plot. Do you remember? And there are various rules related with this. For example, this lambda max, the maximum. Okay, let's turn to lambda. It looks like this also in lambda, right? A bit reverse, but anyways, there's a hump, there's a maximum. And lambda max times temperature is equal to a constant. There are some rules that we have discovered. What is this one called? Vienne's law. Very good. Okay, so far so good. But now we are going to do a classical computation, and we will get a different result. Let me switch back to frequency. Okay. We are going to start by figuring out how do we count modes of light. How do we count modes of light? Okay? So, where are we going? We are going towards ultraviolet catastrophe. Okay? So, to reach there, we need to start simple. Okay? Let's say I have a one-dimensional box. Okay? It's a box of length L. And I'm going to put light in it. And classical electromagnetism, light is a wave, right? So the wave needs to have nodes here because it's in my box. Do you agree? So what is the lambda of this wave? 2L. Does everyone agree? Yes? What is the lambda of this one? L. L. And it goes on like that. So what is the lambda of this one? Two L over 3. So it was 2L over 2, 2L over 1, 2L over 3. Right? So if you look at the frequencies, it's C over lambda, right? So it's going to be C over 2 lambda, C over 2L, sorry. Then the frequency, the next frequency, so lambda 1, lambda 2, lambda 3, F1, F2 is 2C over 2 lambda, and F3 is 3C over 2 lambda. Does everyone agree? Any questions at this point? No questions. So let me plot these frequencies on a real axis. Okay. So I have nothing here. I have 1c over 2l. I have 2c over 2l. I have 3c over 2l, 4c over 2l, etc. Do you agree with this? They are like rooms in a hotel. Okay, the first floor of the motel, and there are rooms. 1c over 2l, 2c over 2l, 3c over 2l, etc. This is F, right? Now, how many frequencies do I have per unit frequency? So dn over df, which is number of modes per unit frequency. Per unit frequency. So, for example, if I choose this length to be my unit, there is only one corresponding to it. Do you see it? Yes? Everyone can count this? So this one is, how long is that one?
C over 2L.
Everybody agrees with that? C over 2L. So I have 1 per C over 2L. So far, so good? Sure, of course. I agree that I have infinitely many frequencies, yes, but they are evenly distributed. Every time I move C over 2L, so this length is C over 2L. Do you agree with that? That length? Yes? Yes. Yes. And inside, every time I get a bar of C over 2L, I count only one mode. Okay? Good? Do you have any questions? No. Yes?
I don't understand why the number of modes are 1.
Very good question. You are saying that it should be 2 because of the polarization, right? No, I'm joking. But it should be 2 because of the polarization, but let's count it as 1. So, why 1? Because there's one point there. That's it. There's one point there. So there's one point here, there's one point here, there's one point here, there's one point here. And I go ahead, I pick a bar that is this long, and wherever I put it, I will get only 1, not 2, right? So for every such a bar, I have 1 frequency only. So far, so good? Now let's move to 2 dimensions. Now I have a 2-dimensional box. Okay, L and L here. For this box, I can have a wave that is fixed at both edges like this. Okay, that's a mode. That would be like just a single hump going like this. Okay, throughout the whole box. Are you following? No? Yes? No? Ask me questions. It's like this. It's like this. Okay, I can't do it. Okay, you get it? Okay, this part shouldn't go up as well. So those parts are, okay. It's like this. Imagine that this is on a square. You understand it, right? Because let me show you the other one. The other one is like this. So it goes like this on one side, but if you look from the other side, it goes still like this. Makes sense? Yes? Etc. So on and so forth. So with the same logic, now my hotel is not just one-dimensional, it's two-dimensional, and there are rooms arranged like this. Okay, so this is the frequency in x direction, let's say it, because it's not really the case, but so in this case, we are going to find the frequency actually by the distance from here, okay? But we will start counting soon. Should I? Okay. It doesn't, this is not necessarily 0, okay? This is not necessarily 0, just plotting. The important thing is the distance between them. Now, let me show you that this one is this one, and it has, this one is that one, this one is that one. And I have C over 2L here, C over 2L here. Does it make sense to everyone? Yes? For example, this one is this one. It's 2C over 2L on one side, but on the other side, it's still C over 2L. Makes sense? Now, let's try to find dN over dF again. I want to find dN over dF again. Okay? Here it was easier. Here it was easier because it was easier. Now it will be harder because let me draw this one again. So what we need here is really this. I have fx's, fy's, and imagine dots, okay, arranged as a grid. Okay, very close by. I want to find dN over dF, which means that I want to find number of modes at a certain frequency. So the way that I do it is the following. Watch this carefully because we will keep doing this. I find a certain frequency and count all the dots that falls within some ribbon, df. So this is like, does it make sense? Because here, but this now is much larger than this distance, so that we actually can make a smooth curve there. Okay, are you following? So let's find how many frequencies are there. How can you find it? 1 over C over 2, I don't think so. Think again. Look, as you look, let me say this is F1, right? If I choose F2, like so, doesn't it encounter less frequencies? So F2 is covering less points than F1. Do you see it? So it's proportional to F. Are you seeing this? It's like students in auditorium. Like it's like an auditorium like this. And the further you go, the more students are sitting there. Does it make sense? So let's figure it out. How can we figure it out? Well, yes. No. Yes, tell me.
Hocam
Yes.
We have total frequency.
Yes. So F is, so that's a bit of a tricky part that needs explanation, but I'm avoiding that explanation. So this is true. Can you take it as holy truth? Hmm? Why not? What should be, like, I have, okay.
Just like a wave on the water. I mean,
Yeah, exactly, like a wave on the water. So if you have a wave on the water that has like this and like that, then it's C over 2L squared plus the frequencies, 2C over 2L squared square root. Okay, the frequency of that vibration will be that. Okay, so Fx and Fy are really not physical things. There is no frequency in the x direction or frequency in the y direction. There is only one frequency of vibration, right? And that frequency of vibration can be calculated by C over lambda x squared plus C over lambda y squared square root. Okay?
So are we assuming that these waves are like behaving like vectors
Yes.
because of this
Yes.
Pythagoras theorem?
Yes. Okay. Are you still with me? So I'm going to actually count, instead of dn over df, I'm going to count dn here. Oops, sorry. I'm going to count how many dn I have here. So, what is that dn? Number in that area. How can I find it? First, I can get that area. What is this area? 2 pi f df, but it's quarter of it, so divided by 4, right? It's just, yes?
If we want to find area, why we are using why we don't use pi over 2 times f?
Yes, that's what it is. Pi over 2 times f. Pi over 2 times f is the length, right? Times df, like the length times the width is the area, right? So far we have found area. We didn't find how many points are there. To find how many points, I can look back at this point, at this picture, and realize that there is only one point in this much area. So there is one mode per C over 2L squared. Did you follow this? The point here is that dn over df is proportional to f. So as you go further in the auditorium, you have more and more frequencies. You have more and more students. Did you follow this? Do you have any questions? No? Do you have any question? Is it boring? Wow. Very good. Thank you. Okay. What do you think comes next? Three-dimensional box. Very good. Thank God we are not in 4 dimensions. Otherwise, it could go on like this. Now I have a 3-dimensional box. And you can, you know the joke, right? Let's assume a spherical chicken. Spherical chicken, spherical cow. It has different versions of that joke. Like an engineer comes to a farm to fix some stuff, and the first assumption is that let's assume a spherical cow. So here we assume a cubical sun. cubical black body, okay? And it will work for everything. Good. Now I have fx, fy. My hotel got three-dimensional. There are floors, and every floor is filled with rooms, right? So I have all these dots that are spread everywhere throughout this volume, and it goes on forever, right? If I want to find what is the number of frequencies, I take something like this. It's like a surface with a thickness of, with a radius of f and thickness of df. Okay? Now this time I know that there are 1 modes per every c over 2l cubed, right? If I multiply it with the volume that I have here, which is 4 pi f squared df, did you follow that? 4 pi s squared df? Because it's, I have to divide it by 8, right? It's 1/8 of a sphere. Then, what do I get? dn, right? Why don't we have what?
C over 2L cubed.
Not c over 2.
In denominator we have.
Why do we have it? Okay. Because we had it here. Okay. Do you see in 2 dimensions we had this one? Like this. Now in 3 dimensions it will be a cube. Like so. Okay? And inside that cube there will be only 1 mode. So far, any questions? Yes.
Didn't we define integral the area under the curve? So here integral to find number of.
Yes, you will find the total number. But what we want is, yes, a number of frequencies, because we are trying to find how many modes we have at a certain frequency. Okay?
So just do one integral for the whole area and the segment.
Yes, you could have done this. You could have done, okay, sorry. You could have done f cubed over 3, and this would be n. And when you take the derivative, it would be f squared df, and this would be dn. Perfect. So far, so good? We are almost there, okay? One last thing. There's polarization. Okay, do you remember the polarization? No? We were saying that because of the polarization, there will be just a 2 coming in front of the equation. We only care about polarization because of that. Where is the polarization? Polarization brings a factor of 2 later on. Do you see it? Okay, here's 2. What is this? This is just, did I just get a message? I hope not. Did you see anything on the screen? Do not disturb. Okay. Polarization. So far, so good? So dn over df is what? Can you help me out with this calculation? What squared?
Pi f squared.
8 pi f squared over 8 is cancelled, but it comes back with a revenge. Yes. So let me leave 1 over L cubed here. So what does it tell you? This one tells you that number of modes per unit volume per unit frequency is 8 pi f squared over c cubed. Do you agree with this? Yes or no? So what? Here's what is what. You have number of modes per volume per unit frequency. What do you want to get? Energy per unit volume per unit frequency. Do you remember? Energy density, we are trying to get this thing, which is energy per unit volume per unit frequency. Yes or no? Do you remember this? Yes. Now, how do we go from mode, number of modes, to energy? No. No, the other guy, Boltzmann. So, let me remind you. Do you remember this vibrating carbon monoxide that we talked about? Every time you have a harmonic oscillator, something that vibrates, you can put KBT in it. Do you remember the money stuff? Like we would share money, and equipartition theorem. It says that each mode gets the same energy. Okay? Good. So we put, energy, du over df is dn over df times kBT. Why? Because we assume, and this is a correct assumption, that each mode is a harmonic oscillator, okay? And each harmonic oscillator gets its own kBT. All right? So what is our classical result? This is it. What it tells you the following. It tells you that the number of oscillators in lower frequencies are a few. As the frequency increases, gets larger and larger number of oscillators, and we have to be democratic and send KBT to each one of them, right? Then we have a dilemma. Then we have a problem. Here's the problem. What we observe this is what we observe experimental. No, that's less dramatic. This is nature. This is observation. I think red is more dramatic, right? Ah, okay. Ultraviolet. Let's go with purple. It goes like this. Because our formula tells us that du over df is proportional to f squared. Okay? It's problematic in whichever way you look at it, it's problematic. All your energy goes to higher frequencies, okay? So to actually keep a system at a certain temperature, you have to have infinite energy, because there are infinitely many modes. It goes on forever. Nothing can stop it, okay? So that's the ultraviolet catastrophe. Okay? Are you with me?
John,
Yes.
Why did you say that the polarization factor of 2 was coming? Where did it come from? Like, why did it come?
Why did it come? So if you remember, so this is the wave, but it could have an electric field pointing this direction, an electric field pointing in this direction. That's 2 options. So they are 2 distinct modes. Okay?
So we need to consider 2 of them?
Yes. Okay? But like could be million, could be 0.1, doesn't matter. As long as it goes with f squared, we are doomed. We have the catastrophe. Because f goes forever. There's nothing cutting, there's no cutoff of frequency. Right? And those modes are there. Classically, they are there. Do you see the problem?
So for every wave, we can observe that. Why it's called ultraviolet catastrophe?
Because we were observing the spectrum coming from light, from sun, sorry. The spectrum of light that comes out of the sun, and we were seeing this. So as you go to ultraviolet regime, it goes to infinity, right? So that's why it's called, that's why we are thinking about it in terms of light. Okay? Good. Now comes the solution. Okay? Unfortunately, I have only 10 minutes. So wherever we stop, we can pick up later on. Okay, take a deep breath because I think Planck did too. Planck's solution. Let's say Planck's solution to this problem. So Planck came to the scientific community and said, I'm going to say to you something crazy. Okay?
And simple.
Hmm?
And simple at the same time.
Simple at the same time, which solves our ultraviolet catastrophe problem perfectly.
But you don't like.
But it's ridiculous, it doesn't make sense, etc. Okay? So, he says, here is the solution. Do you remember we said that everybody gets KBT? He says, let's remember why we said that. Okay? We said that because these are harmonic oscillators. Right? Harmonic oscillators can get any energy they want. Do you remember the money thing? You give 10 liras, they accept it. 100 liras, they accept it. Everybody is like that, okay? Those are classical harmonic oscillators. They don't care whether the money is low, whether the energy they are getting are low, high, etc., right? So, what is the probability of them getting an energy of E? This is the probability. Do you remember this probability? Yes? Good. Then let's find the average energy they are going to get. I multiply probability with energy and divide with all the probabilities. So I'm taking the average with respect to Boltzmann distribution. Did you follow this? What do I get? I do get KBT. If you do this, you get KBT. That's our famous KBT. Okay? Do you have any question here? Have you resolved the problem? No, right? KBT is KBT. This KBT is that KBT. Nothing new happened yet. Now, he says, okay, I know you will hate it, but let's say harmonic oscillator can't have any energy, but for some reason, it depends on its frequency. Okay? It depends on its frequency like so. This is my constant. This is an integer. And this is the frequency of the oscillator. Do you see this? Why he was worried? Because it doesn't make sense. Okay? Can I pull harmonic oscillator this much? Yes, you can. Can I pull it a little bit further? Yes, you can. Why on earth would it not have any energy? One. Why on earth would it be related to its frequency? Right? But he says, wait, what happens is really nice. What happens is this. You calculate the same energy, the same formula, but this time you use this NHF e to the minus NHF over KBT. Oopsie daisy. Of course, this is now a sum, right? Okay, did you follow this? Same formula, just the energy is discretized. What do you get? You get HF over e to the HF over KBT minus 1. Okay? And you plug it in. Should have used a different color for this. Let's use red. Okay. So, if we follow this, then du over df is same counting. I still have 8 pi f squared over c cubed time. Now, this time it's not kBt, but it's hf over e to the hf over kBt minus 1. Okay? Very good. Did it get worse? So let's copy this. Paste it here. So if you plug in this formula, it's like this. Exactly fitting the observations. By putting it, by fitting it to the experiment. Okay. So that's where, that's how quantum mechanics was born, actually. From a crisis. Of course, it was forgotten immediately, I think, because it's really, really crazy. The problems it produces are much more than the problems it solves, right? All right, let's talk about it a little bit. So what's happening physically? What's happening physically is that before you would accept a mode would accept any energy at all, okay? Now, let's say, which one is higher frequency? So blue is 440, right? It's higher frequency, right? So let me just paint it in dark, this one. So this is classical. Now, in Planck, the blue one has higher frequency, so it accepts only these energies. Okay? The red one accepts these energies. Okay? It is as if you insist on getting $500, no less. You are at higher frequency, there are more of you, right? But as you go in the frequency, you demand more money to kick off, to accept it. You just don't accept anything less than that, right? What happens? $500 never comes together so that you can pick it up, okay? It's exponentially less likely while you are with square amount larger than others. So as f increases, the number of modes increases with f squared, right? But the probability of getting the kickstart energy for them decreases exponentially. You see it? As a result, there are infinitely many of them, but they never get excited. Does it make sense? This is pretty much it. Do you have any questions?
Was that idea accepted?
What?
Was that idea accepted?
Yeah. You will see it accepted. It will solve more and more problems and will create more and more problems, but we will be forced to accept it as a new theory because it just fits. It has been like that since Newton. Like Aristotle's law, right? Like push it, it will move, stop pushing, it will stop moving, right? Newton's, this makes sense to our minds because we evolved in dissipation. Okay. Let me make my point and then we are finished. But then Newton comes and says that even if you stop pushing, if there's no friction, it will keep moving. It's quite counterintuitive, but we see it works and we have nothing else. Same with quantum mechanics. It keeps working. It produces problems of interpretations, but we are still struggling with them. But this is the best theory that we have. Okay. Take care.